Right, so welcome to REScipe. Next, please. So our project's goal is to map a food image to a recipe. And we want to do this because we want to motivate more home cooking. So when people browse social media or the internet and they see food images that don't have an attached recipe with it, but they still want to make it, that's what our project aims to help support. And we chose to use neural nets because recipe images are just highly varied in nature. Next, please. So here is a standard input output. So on the left, you can see a food image, and what we want is we want to output essentially the recipe. But for qualitative purposes, we have our essentially a database of recipes. They have their own titles and their own corresponding recipe images. So we will be doing qualitative results with the recipe images instead of just outputting text. So next, please. So here are some of our qualitative results. As you can see, every left image is the test image and every right image is the recommended recipe image. So as you can see, we have a decent number of good qualitative results for certain food groups or food categories. However, since our test data was out of distribution, a lot of our images were mainly between mediocre and bad. Next, please.
And this is the pipeline of our project. First, we use a data crawler to crawl data from allrecipe.com. And then the data goes through a data processing progress. The image got resized and we apply data augmentation. And the recipe title, we use those to train our LDA models. And we use that to generate low dimensional labels. For the neural network, we use a pre-trained CNN to pre-process the image into feature vector and use feature vectors to train the fine-tuned models. For evaluation, we remove the last layer of the NN models and use a smaller model to create a lookup table from the data sets. And this is used to find the most similar recipe vector for the new image. Next.
For our data, we used a Python package to scrape all the recipes, obtaining a raw data set that contains information such as the recipe titles, the ingredients, and the URLs to the corresponding images, as seen on the bottom here. Next.
So there are two types of data we need to process. For the first type, for the recipe title data, before we process, we need to visualize them. Here's the top 50 most common words that appears in the recipe titles. For now, we see that although they are imbalanced, most of the common words in the top 50s have similar distributions that is still good for training the LDA. Next. Then we go into the data processing. For the NN training, we need to reduce the dimension of the recipe titles. So first, we tokenize them, lemmatize them, and remove the infrequent words from the recipe title, and then we convert them into TD-IDF representation. And then we can use the representation to train the LDA model for topic modeling. And then before that, we filter our recipe with unrepresented topics. Next.
We processed all of the images by first filtering the default images, and then we resized the usable ones to a trainable size and added data augmentation, including image cropping and color changing. Next. For our final data set, we split it so that we have 40,000 unique recipes for training and validation, and as well as another 1,000 unique images for doing the testings. Next.
For our MN model, we use a CNN. The pre-trained model we use are ResNet 34, ResNet 50, and VGG 16. When we are training, we freeze out the convolutional layer and remove their fully connected layers and replace them with our own fully connected layers. And then we apply training on the baseline and on the ResNet. Next.
For some statistics, we used a cosine similarity for our accuracy metrics and set the threshold to 0.9. And for our baseline VGG, we have a 70% validation accuracy. And for the ResNet 50, we have a 60% accuracy. However, on the bottom, as you can see, the test accuracy generated by this cosine similarity is really low, and it's much lower than the qualitative description we have. And this is because the test dataset is out of distribution, and the model has never seen the label vectors of the test images. Next.
So what are some things that we came out with? So we realized that our model does weigh image similarity a lot more than the actual recipe title inferencing. And some of our model outputs appear a lot more frequently, such as the chocolate cake, as you've seen before, appear about like 15% of the outputs. VGG in our case actually performed better than ResNet. We speculate this is because the output from ResNet pre-trained layers were too tightly, all the feature vectors were too tightly clustered. And overall, our data distribution and raw data wasn't the best to work with but we kind of expected this since we did source it from online websites. And some things to try next time is to use maybe ingredients and glove vectors, and maybe retrain some of the pre-trained layers in ResNet to help generalization. And yeah, that marks the end of our presentation. We welcome any questions.
Great. What was that last? You didn't say the last comment about.
Yeah, no, those it was more like a frustration thing because like Colab just has its own like specific issues that we just had to deal with. So we were hoping to move out of it.
But there's two big ones I've heard of. It's you just lose it after 12 hours. Can't have more than that. But also,
yeah,
with people with images, the first load of the images is a big deal. It seems to take forever to get it in.
Yeah. The caching of the RAM.
So we loaded different data into chunks and save them as different files so that the thing doesn't crash.
Yeah, and there may need to be. Yeah, somebody's gonna have to rethink the whole Colab thing and cloud thing. There were other issues with cloud too. Yes, and learning to use cloud would be fantastic. Okay, so I need to try to understand something. I need to go back to this pipeline, and I didn't understand it. Let me see if this is about creating the data set. The data set has both. Oh no, I'm confused now. There's the tokenized. This is just the name of the food. So
yeah,
chocolate cake
title.
Yeah. For each recipe, the recipe has a title name and there's a corresponding image with the recipe.
And that's what these two paths are. Okay. So
yeah.
And so the input is the.
So basically, we just attach these additional labels to the original, to each of the original recipe.
Okay. And what's the 6 images?
The 6 is the data augmentation, the additional image from data augmentation.
Oh, I see. And this is not glove vectors. This is LDA vectors. Is that right?
Yeah. We did the research. We found several examples about using the LDA model to create from the TD-IDF, but we didn't find much research about like how to actually apply a glove vector.
I thought those words would be in the vector set. Okay, so then this is, so there's 2 pathways, one that deals with the image and one that deals with the word. And so this is, one of those ResNet things you were talking about. And then this is sort of, it's confusing. We got the label vector here, and then
the top one is the output from the ResNet kind of the CNN layers, so excluding the FC layers.
Okay. And so that's this feature vector. Okay, it goes into, so this is the fully connected layers here.
Mm-hmm.
And then that gets you, but this is going into a label vector. It's confusing. That's what's going on here. I don't get the.
So the upper feature vector is the input created from the convolutional layer of the residual network or the VGG. And then it's trained to predict the label vector.
Oh, it's trying to predict this. So there's some loss then.
Yeah, the loss is applied as the label vector.
I see.
But after we finish training this, we remove the last layer.
The last layer of
the
MLP.
Basically, remove where the label vector layers is.
Okay, and it just predicts something that then you take over here.
Yeah, we basically take the second last layer and to produce like.
And this is where you do the cosine similarity. Is that right?
Yeah, yes, that's the cosine similarity.
So yeah, we store all the finalized feature vectors in a database, and then every time we get
no. So don't start talking about something else that I'm not asking about. I'm just trying to understand this. So that you do the cosine similarity here, and that's how you select the answer. You pick the nearest one. Okay. It's hard to follow that. I haven't read your report yet, so I didn't. That's the first I've really seen of this. Okay.
Yeah, the pipeline is really long, so.
Yeah. But, you know, figuring out how to explain things clearly is tricky. That's part of the whole point of this course, actually, among other things. So, okay. How much time? Oh, I'm okay. So now that lets me go back here. You use the word out of distribution for your test set. Why is your test set out of distribution? Shouldn't it be? It should be things that have not been trained on, but it should be within the distribution. That's a fuzzy concept. But since you're using, I mean, I know the concept, and it's a really important one. It's one where people have wrecked in this course before. They pick completely unrelated and dissimilar kinds of pictures in the test set compared to the training and validation sets. Why are you saying that happened?
I'm guessing it's because the inputs come from different users, and like different cameras, different specs. So essentially, every image or every input is different.
It's so different
that
than mode of distribution. Yeah, but that's sorry. How many total items are there? What's the size of this data set?
Around 400, over 40,000 unique ones.
The number was 46,000 recipes, and we generate like multiple augmented image for each recipe image. So the data set go up to
6 times that.
25. Wait.
Yeah, you did 6.
250. Yeah, 250,000.
Yeah, so I don't know that I buy the out of distribution point. It just might mean that it's a hard problem. And well, let's see. Is there any evidence of overfitting? Have you got a training curve here?
Yes, we do have that, but we didn't put it in the slides. It's in our report.
Yeah,
I think
we're looking at here, not that.
The resonance overfits really hardly.
Oh, but you don't have your method, which I like that your method is not simply a neural network, right? You've got the cosine similarity thing at the end. So that's that could be the source of an issue, which is whether cosine similarity is the right way to go with respect to this. Oh. Did you ever plot the outputs of those? This is really interesting. It's not an easy problem that you try to solve. Did you ever plot some version of these feature vectors? Have you ever seen people do this with words? Have you ever seen these kind of two-dimensional plots of words that are word vectors that are really 300 size, and they kind of map them down to 2 or 3?
So like teasing?
What's the word you're using?
Like TSISNE, basically like reduce the dimension to plot it.
Various kinds of dimensionality reduction. Did you try?
Yeah, unfortunately, we didn't actually get a chance to do that.
Yeah. I guess that might give you a hint as to whether it's hard. It's always hard in these many dimension outputs, but it might give you a hint about what might go right or wrong. Okay, really, really interesting. I actually like that you did that. It's a great example of one thing I hope the message has come across in this course, which is, the neural nets are one piece of this, but you are going to be trying to solve interesting problems, and the real exciting work comes when you focus on specific problems and then start using your other knowledge, like, even from your algorithms and data structures course, that might show up as a piece of something you need in a real solution. So I like this for that. Shashik, any comments, questions?
Yeah, so you said that during testing, the out of distribution images, so I was wondering what was the predicted recipe for your test images? I mean, you said that one of the prediction was dominating the test set.
Yeah, if you go to a qualitative results slide, you can see the bottom right, the cake. That was the one that dominated, or just appeared a lot more frequently. And we say this in the report, but we presume that this chocolate cake, like the feature vector, was like very far away from the other clusters of feature vectors, so that, and if our model didn't generalize very well, essentially all the inputs that weren't in these tightly clustered feature food groups gets mapped to the cake instead, because it kind of monopolizes the feature space.
Oh, so then if you're saying that, then it should have been nice to visualize the feature vector on some 2D space. and then you could see.
Yeah, maybe if we had more time, but
Yeah,
mhm.
that's. Otherwise, it looks good.